Let's say our function is x squared, and let's not say what a and b are. Let's leave a and b unspecified. Unspecified, other than to say a is still less than b, otherwise I wouldn't write the interval. Delta x is still going to be b minus a over n. Xi is still going to be a plus I times delta x, a plus I times b minus a over n. Let's go ahead and compute a right-hand sum in this abstract situation. Let's see if we can do it. Or let's see if I can do it, I guess. Can I do it? Can I do it? All right. Xi, this thing has got to get squared because the function is x squared. Our first unpleasantness. A plus I times b minus a over n squared. Delta x is b minus a over n. I could leave the b minus a over n as a delta x for a while and just replace it with b minus a over n at the end. Well, let's do it this way. I goes from 1 to n. Okay, I have to square this. And maybe I want extra parentheses in here just to emphasize some things. Square this, I got to FOIL it times itself. Can you imagine doing that? A times a would be first times first, a squared. Outside times outside and inside times inside would both be the product of these two things, and I'd have two of them. 2ia times b minus a over n. And then last times last is going to be squaring this thing. So I get an I squared and a b minus a over n squared. That all has got to get multiplied by b minus a over n still before I bring the summation sign through. Oh, let's see here. Use the distributive property. Bring this through the parentheses. So we got, oops, go back to green. A squared times b minus a over n plus 2ia b minus a over n quantity squared. I'll write that as b minus a squared over n squared. And then times this gives me an I squared b minus a cubed over n cubed. Bring the summation sign through. It's really the commutative property. So I get this summation. And with the other summations, I think I'll also factor out anything that doesn't involve an I. So I'll do this. Make sure you're copying what I write here correctly and don't make a mistake. Wow. Have I made a mistake? I think I'm okay. Stuff does simplify here. This summation is adding up a constant because there's no i's. I'm adding up these things n times, meaning the n goes away effectively when I simplify this. It simplifies to a squared times b minus a, or if you prefer, a squared b minus a cubed. Because, again, I'm adding up these things to the right of the summation sign n times. You could factor the entire thing out and have a 1 there. And this whole thing there would get multiplied by n. The n's cancel is what I'm trying to say here. With this one, that gets replaced by our friend from 5-10 minutes ago. That's n times n plus 1 over 2. A little bit of happiness happens in that the 2's cancel and 1 n cancels. Oh, but what do we do about this? Let's ask Mathematica again. Mathematica. What do I get if I add up a bunch of I squareds instead of i's? So I'm adding up perfect squares is what I'm doing. I'm doing 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64. Is there a formula for this? Yep, there it is. More complicated. N times n plus 1 times 2n plus 1 over 6 is what it equals. Do get a little bit of cancellation. This n cancels with one of those. We're making progress. I think we're getting close. We're almost ready to let n go to infinity here, I think. So what do we have here? A squared b minus a cubed plus a times b minus a squared over n times n plus 1 as well. Don't forget the n plus 1 there. And then plus, let's see, b minus a cubed over n squared times n plus 1 times 2n plus 1 all over 6. Hope I have not made a mistake. Now let's let n go to infinity. The integral should equal the limit of this as n goes to infinity. Let n go to infinity. All this goes to what then? Well, that's just a constant there. It's a squared b minus a cubed. What about this? Well, it's a rational function of n, really, where the numerator, the n plus 1, has the same degree as the denominator, n. Look at the coefficients, 1 there, 1 there. This part goes to 1 that I'm circling here. So I'm left with that. As n goes to infinity. And what about this one here? Once again, this part's a rational function of n. The degree of the top and the bottom are both 2. The coefficient of n squared is really 6. Coefficient of n squared on the top is 2. This goes to 2/6, or 1/3 as n goes to infinity. And then you also have the b minus a cubed there. Looks like this is going to go to that. That's the answer, evidently. Okay, let's see if we can simplify it. A squared b minus a cubed plus, if I multiply this out, it's b squared minus 2ab plus a squared. Multiply the a through, I get plus ab squared minus 2a squared b plus a cubed. And then I got to expand this with Pascal's triangle, say. That equals b cubed, I'm looking at this row here, minus 3b squared a plus 3ba squared minus a cubed. You have to alternate the signs, plus, minus, because of the minus sign in there. And then I'm also multiplying that by 1/3. So I get plus 1/3 b cubed. The 3 and the 1/3 cancel, so I get a minus b squared a plus ba squared minus 1/3 a cubed. We're getting close. Combine like terms. Does stuff cancel? Looks like at least one thing cancels here if I have not made a mistake. Looks like this cancels with that. I was kind of hoping those two things would cancel, but oh, wait a minute. Oh, the a squared b terms all do cancel because there's three of them. This, and this all cancel because there's plus ones there and minus two there. This is simplifying quite a bit here. What's the a? The a cubes cancel here and here. This simplifies quite a bit to 1/3 b cubed minus 1/3 a cubed. Something fairly simple. Now, what's the real reason that I did this, other than just to enjoy myself? Two other reasons. One of which is to emphasize we can do it with a limit, though it's very complicated. Another thing is to relate this to the fundamental theorem of calculus. What does the fundamental theorem of calculus say in this context? FTC stands for fundamental theorem of calculus. We had the MVT was the mean value theorem, and the RTP was the racetrack principle, and the CFT was the constant function theorem, and the IFT was increasing function theorem. Now we've got the FTC, fundamental theorem of calculus. You might want to write that out. Says that to do an integral of a function f of x, I don't have to do a limit. Hallelujah. I don't have to use limits. Just like with derivatives, even though derivatives are based on limits, we can calculate them with derivative rules, product rule, quotient rule, chain rule, etc. Likewise, with integrals, you don't have to do a limit. All you need is an antiderivative of little f, and you're almost home free. Call an antiderivative capital F. You just do capital F of B minus capital F of A, where capital F is an antiderivative, an indefinite integral of little f. Let's write that by saying capital F prime of x equals little f of x. Capital F is an antiderivative, an indefinite integral of little f. What's an indefinite integral of x squared? I could have put this on the exam. You had a problem like this. It's 1/3 x cubed plus c. Oh, boy, it's feeling really close here, isn't it? But what about the plus c? It doesn't matter because when you subtract, it cancels. If this is my capital F of x, then capital F of b minus capital F of a is 1/3 b cubed plus c minus 1/3 a cubed plus c. Distribute the minus sign through. The c's cancel. We got the same answer, 1/3 b cubed minus 1/3 a cubed, using the fundamental theorem of calculus. No limits necessary. Wow. That's Newton and Leibniz's astonishing discovery. That right there is the origin of calculus, right there. I said this a week ago, I think. People were figuring out areas 2,000 years ago, although they were very special areas of squares, rectangles, triangles, circles, ellipses, and surface areas and volumes of spheres and cylinders and so forth. People were figuring out tangent lines and slopes before Newton and Leibniz came along, before they were even born, in special circumstances at least. What Newton and Leibniz discovered, Newton around 1670, I think, Leibniz around 1680, the Leibniz published first, was that areas and slopes are interconnected. That's the astonishing discovery. We can find areas by inverting the slope finding process, finding antiderivatives instead of derivatives. Use a function capital F whose derivative is little f, the integrand function. Use an antiderivative and just do a difference. No limits necessary. Astonishing. This should seem like magic. It still seems like magic to me, but this works. It's astonishing. However, there is a way to view this that we'll see Wednesday and Friday that makes it actually intuitive and makes it almost obvious why this works. And thinking about the dx's as infinitesimals and imagining, where's my integral symbol? Imagining f of x dx to be a multiplication and the integral sign to be a summation, even though that's not really what's going on, is helpful and makes the fundamental theorem of calculus almost obvious. At the moment, it doesn't feel almost obvious. It feels like magic. Poof, out pops the answer. Just use an antiderivative. The c doesn't matter, and so we could just use c equals 0. And that's the most common thing people do. The most common way to show work to do the integral that we were doing there, the definite integral from 0 to 10 of x squared dx, is to write an antiderivative here, 1/3 x cubed, plus c, but take the c to be 0. Don't bother even writing it. You don't need it. You do need it for indefinite integrals because it's useful for differential equations. But for definite integrals, you don't need a plus c. I mean, it doesn't hurt because it cancels, but you don't need it because it cancels. Put the limits of integration here over here on the right, 0 to 10. I'm saying the definite integral of x squared from 0 to 10 equals the evaluation of this antiderivative from 0 to 10, meaning plug in the top number and subtract what you get when you plug in the bottom number. I'm doing 0 to 10 here for A to me here. This is like the example from a week ago. 10 cubed is 1,000. Oh, this is our old friend, 333.3 from a week ago. Out pops the answer. Now we're running low on time. Let's talk about some other things here. I could have done all this with a left-hand sum instead of a right-hand sum. I could have used left of n equals summation I goes from 0 to n minus 1 of f of xi times delta x. For any fixed value of n, this does give a different answer for the approximation to the area. However, in the limit as n goes to infinity, you get the same final answer for the exact area. I could have done a trapezoid sum as well. I could have taken the left and right-hand sums and averaged them. For any fixed value of n, you're averaging the left and right-hand sums. This is probably a better approximation to the integral for any fixed value of n. And in the limit as n goes to infinity, since left and right both go to the same thing, 1,000 over 3 in the example I just did, it'd be 1,000 over 3 plus 1,000 over 3 over 2, which equals 1,000 over 3. The average of two numbers that are the same number is the same number. It still goes to the same answer. You still want to be able to think about doing your work and interpreting the integrals in terms of areas and signed areas. That's just like on the homework you had today. That still comes up. You'll be thinking about upper sums and lower sums, whether your graph is increasing versus decreasing, which is going to give you an overestimate, which is going to give you an underestimate. You should be able to think about errors. Problem solving video can help again. Okay. But I think it was important to do what we did today, even though it's not explicitly like your homework. Could show up to some degree on exams, and it's good to know about this stuff for the purpose of understanding calculus better. Not perfectly, but better. Okay. Have a good day.